My name's Andrew Grimshaw. I may or may not be familiar to this community. Up until very recently, I was a professor at the University of Virginia. I've worked on a number of projects, and now I'm working on something that I'm very passionate about, and that's building green, low-cost cloud computing centers in the Great Plains of the United States of America. And why that's the case, hopefully, will be pretty obvious in the next couple seconds. I'm using a new set of tools, and they're slower than my old tools. So I'm going to talk just one slide on Lancium, where we come from, about our campuses, and why we're building them the way that we are. I'll then talk about Lancium Compute, our experience with OSSG in the last year, and it's been a lot of fun working with Brian and Mats and everybody else. And then I see what happened. They put it. I don't want to make excuses, but we just got this new corporate look deck on Monday. And so I had to shift everything over, and some things have screwed up. We'll talk about CCSTAR and then simple discussion. I'm waiting for it to transition. There we go. So Lancium basically is all about enabling faster decarbonization of the electrical grid. That's the corporate mission. That's what everybody in the company is completely bought into. But to do it in a way that's economically feasible and sustainable going down the timeline. So the company was established in 2017, at Supercomputing in 2018. Our CEO, Michael McNamara, and Ray Klein, who some of you may know from his days at Sandia National Labs, came to Supercomputing and asked me a bunch of questions. I thought some of their ideas were, to be honest, a little bit on the fringe. And I said, well, I'm not going to go work for you, but I will consult. And I did that through March. And then I joined the company full-time and took a leave from the university in June of 2019. We closed recently in November on $150 million Series B. And that sounds like a lot of money in this community. But if you haven't built large-scale electrical distribution networks, you don't understand how expensive equipment can be in that space. Transformers are huge amounts of money. So we just received our Series B, where the vast majority of the power at our data centers will be renewable, wind and solar being the dominant life forms, and that's what we will have. And over the next 2 years, our plans are to build out approximately 2 gigawatts. That's gigawatts, not megawatts, of data centers in the West Texas load zone. It'll be mostly Bitcoin, but there will be some non-Bitcoin, and I'm hoping to reduce the amount of Bitcoin and increase the amount of computing, because I think that's a really cool idea. It looks like there's like a 4-second lag from when I hit page down, 5-second lag. So let's take a look at the campuses. Wow, this slide deck is slow. So basically, our data centers are going to be mostly Bitcoin. We're willing to host hyperscalers. They have to provide their own equipment, and then high throughput computing. We locate these in areas that have a high density of renewable energy. We can get power, what are called PPAs, power purchase agreements, with renewable providers. One of the primary attributes of our data centers is they have to be rampable. That's because if we're going to incorporate more renewable energy into the power grid, it can't be projects that use a constant amount of power, because the fact of the matter is renewables don't generate a constant amount of power. So you need to be able to manipulate your load in order to make the most effective use of the stuff that's there. At the end of the day, we end up with an all-in electrical rate that we can give to our customers, depending on the quality of service they want, of between 4 and 6 cents a kilowatt hour, and that's all in, and that's at the facilities. I'm waiting for it to go down. Oh, it went down to, no, it did not. So let me give you some motivation for what's going on. I got to make sure I didn't, yeah. So I don't have a chart on here, but this sort of alludes to the chart. If you look at the bottom left quadrant, it talks about west wind and west solar. So this is saying how many megawatts of wind and solar were available in the Texas West load zone in the different years. And one of the things to keep in mind is that if you look at those numbers, it's ramping up very quickly. Many of you are almost my age or older, and remember the days of nuclear power plants when electricity would be too cheap to meter, and where a typical nuke plant was about 1 gigawatt. What you see here is just in the last year, you know, we added something on the order of 5 gigawatts of wind in that load zone, and another 3 megawatts of, gigawatts of solar. And next year it's even larger. And in the next several years, the amount of renewables in the Texas West load zone will approach 60 gigawatts of nameplate capacity, which is huge. To put this in perspective, the state of Virginia in the winter uses about 6 gigawatts, the entire state. And in the summer, we use 28 gigawatts. So we're building, not we, but the society is building more renewable energy in West Texas than many states use. And this is driven by the fact that renewables are now the least expensive way to produce energy in the world, period. They're just the cheapest way to do it. The problem in Texas is common across many areas where there's a lot of renewables, and that's a problem that's called congestion. And the problem is that you have all this electricity being generated, but you only have 15 gigawatts of wires to get it out. And when those 15 gigawatts of wires are literally exactly 16 wires that carry all that power, that's it, there's no more. And so what happens in the marketplace when that occurs is that the turbines don't turn, and the solar panels get turned off. And it's called being curtailed. And so what happens is, if you're a wind generator in West Texas, 48% of the time, you're told not to produce any power because there's no way to do anything with it. And that potential energy just gets dropped on the floor. And so there are terawatts of electricity in the Great Plains, Texas in particular, terawatt hours of electricity that is literally just being thrown on the floor, despite the fact that every megawatt of electricity generated in this country on average leads to the production of 700 kilograms of carbon dioxide. So this is sort of the situation that we're operating in, that we're trying to leverage. Let's wait for a second here. Come on. So it explains why that happens. So on the left-hand graphic, you'll notice that Texas, there's a bunch of little dots. Each one of those little dots is a substation, and prices for electricity are calculated at the substation. And this is the average price in 2019 of electricity in these different substations. And what you'll notice is the dark sort of blue, if you see blue the way I do, is about $10 a megawatt hour. And the teal is coming up on 20, and the red is around 30, 33, and so on. And you'll notice that all the cheap power is to the upper left, and all the expensive power is on the bottom right. And that's because there are 16 wires that connect this part of the world, and they can only move 15 gigawatts over that. So it's pretty obvious, if you want renewable power and you want inexpensive power, you build on the left-hand side of that line and not on the right-hand side of that line. And that's exactly what we're doing, is we're exploiting the fact that there's an absolute surplus of energy in that quadrant, and we can get it for very little money. By the way, now it's about to go away. I'm going to go back a slide. If you're really interested in how having a flexible load can improve the state of onboarding of renewables, just Google UVACS Grimshaw Renewable. I have a talk in there that explains how the electrical markets work. What are some of the critical factors in grid stability? You can't just bring on a lot of load unless you can keep the grid from crashing. And there's having a flexible, controllable load is one of the most critical things in stabilizing the grid. So in essence, by having our ability to ramp up and down quickly, and I mean within 15-second time windows, we can help stabilize the grid, which allows more renewables to come online. So that's electricity has been something I've learned a lot about, but the pace at which this stuff is coming on is kind of staggering to me. Okay, so we're building data centers in Fort Stockton, Abilene, and Childress. And we're also going to be building a research facility at TTU in Lubbock. And all of these sites will have 100 gigabit per second minimum networks. And essentially the three sites can have the capacity to go to 2 gigawatts of power. And basically we're limited by the rate at which we can bring that stuff online. And the first ones will start coming online late in this year, early 2023, and it will go up in 48 megawatt chunks. Our current data center is in Houston, which I'm circled in red because Houston uses fossil fuels for the most part. We buy carbon tax credits, but in my opinion, that's not really being renewable. What's really renewable is the stuff we get at those other places. But we have tons of power available. It just literally tons of power available. So we have all this power in the Great Plains. And I think that running science and engineering applications on all renewable infrastructure is a really cool idea. And that's sort of what I'm here to talk to you about. So the first couple minutes here was to try to explain to you that in the Great Plains of the United States and a few other places in the world, the amount of renewable energy that's coming online will just blow your mind in terms of what's there. And it's so cheap. There's actually 10% of the time in West Texas load zone, electricity is negatively priced. So they pay you to take it. It's a really interesting situation to operate in. Okay, so let's look at Lancium Compute Services, what we've been working with the OSSG team on. We basically do two types of services. We do containers. We use singularity containers. That seems to be what this community wants. I think of it as a remote command line service because in essence, what you do is you register your container and then you say, I want to run this container. Here's the command line. Here's the data that it needs to have to run. Here's what you need to stage in. Here's what I want staged out post execution. You tell us how many cores you want, how much memory, do you want a GPU, what kind, that kind of stuff. Essentially you give a resource specification, essentially, you know, an advertisement. And once again, in this community, the notion of matchmaking and things like that is going to be very familiar. We find a resource to run that on and we run it. Along the way, we have to handle a lot of data. People can put their data either into our storage environment and stage in and out of that storage environment, stage in and out of their own environment, or the way that OSSG is doing things right now is they just go out from the nodes and get the data wherever they've stored it, and we just get out of their way, and that seems to work really pretty well. I have to get this timing down. Wow, that's slow. So Lancium Compute Services, we targeted the high throughput computing market. High throughput, you know, single node, well, single core, single node, low degree parallel applications up to 90 nodes. We now support MPI. And the reason is because high throughput computing, what we need are applications that essentially are operating in offline batch mode and don't interact with human beings or other programs really. And that's because we sometimes are going to need to suspend jobs or persist them down to disk and then restart them again later. We've developed some technology working with the Singularity team at Control IQ and with somebody at Northeastern so that we can take an application running in a Singularity container and persist it to disk and migrate it and restart it on another machine at another site without the application programmer having to do anything to their application. And this is really important because being able to persist a running job in the past has needed basically meant the application programmer had to write that. That's no longer the case. We can just do that. So what you do is you register your container or use our pre-configured ones, and then you can use a CLI as the example here on the right, or you can we have a REST API. You can do that as well. We also have a web browser, but that's really awkward for high throughput computing. So in the example on the right-hand side, we have a LCLI job run. The name of the job is blast tutorial. The command line is blast T with some parameters that I can't tell you what they do very well. And then the image name is Lancium Blast. We wanted 4 cores, 8 gigs of memory, input and output. There's no output file here. It returns it in standard out. And we run. So basically you can do all the things you can do in a classic batch queuing system. You can submit jobs, you can monitor jobs, and you can terminate jobs. It's about 6 seconds. In terms of data, staging is pretty much what you would expect if you've been doing this for a while. You can specify files that will get staged into the job working directory pre-execution. From your site or the Lancium data centers, and then post-execution what you want staged out. This is if you're not doing your own wgets and stuff like that. Lancium storage, everybody who has an account has a directory, like their home directory, where you can put and get data, and it can be the source or the target for job execution, and it can hang out there. There is a way to hook into your campus file system. We developed this stuff under Exceed. That's sort of requires somebody on the other side who knows what they're doing with Linux and firewalls. And so most our customers don't mostly do that. We also have a read-only cache where you can specify a subdirectory in the storage area that I just talked about, and specify in your job that you want that. And what it will do is it will make a read-only copy of that data that will be NFS mounted into your environment. We divide our systems into what we call subclusters. Instead of one big machine with one big hard to manage and expensive parallel file system, we just have a bunch of subclusters. Each head node has 14 terabytes of transient scratch space for running jobs. That gets mounted, NFS mounted into the container on the compute node. And we do all the job staging in and out of that environment. So when you start running in the container, your current working directory will be in something called /jobdir, and that's where data gets staged in and out of. Each node has approximately 860 gigabytes of local scratch that gets mounted in your /temp. That's what we're doing with OSSG right now. Their /pilot gets mounted into temp, and they have 860 gigabytes of local scratch. That has the advantage of taking pressure off the shared file system, obviously, but it also 860 gigabytes of scratch space is enough for most applications. We also mount the CVMFS in every Singularity container, and we have Squid and Frontier services available if you want to use those. Coming up on, I think that's all there is about that. So in terms of business aspects, we don't charge ingress and egress fees. We do firm contracts, which basically means you can send us a purchase order, say no more than this. And if you run over whatever you specified, well, we eat that. So we eat the risk on that. Our rack rate, which is the guaranteed you'll never pay more rate, is a penny a core hour and 10 cents a K80 hour and $10 a terabyte a month for persistent data. We have currently 2 quality of service models: on demand, basically once you start running, you'll run, and best effort, which basically says when we can kick you off at any time. And there's going to be 2 best effort modes when we get to the next phase, where you can either ask to be terminated, which is what OSSG would want, I'm expecting, or where we persist your state to disk and restart you later from that disk space. We have the technology in place, but not all the business stuff in place to do through 4 levels of quality of service. On demand basically means once you get all of your job stuff up, we start it running, and it will stay on processor till the end of days, if that's what you've told it to do. A 50%, a 25%, and best effort. And this takes a little explanation. If you tell us your job will take 10 hours and you ask for 50%, we guarantee you that you will get 10 hours on a CPU in the next 20 hours. That's a guarantee. And so what that means is if you can wait a little longer, you can save a lot of money. And then similarly, 25% is you will be on 1 in 4 hours as a guarantee. And best effort, we make no guarantees. It's just whatever's available. And there's significant QoS volume and prepaid discounts, just like all the other vendors. I may actually finish early, which I just came out of doing another set of presentations, and I had to talk really fast in those. So what have we done with OSSG? It's been we started running a little bit over a year ago before we got much equipment. I'm waiting. So I look at OSSG as a poster child, for the kind of load we want. I mean, we couldn't have picked a better partner in terms of, they do exactly what the kind of jobs we want to do, interruptible jobs. So that's what we've been doing. We've been running Squid servers for them. Our production Singularity container that we run with OSSG, we didn't develop. We helped debug, I think it might be a better phrase, with Mats and Brian to make sure that we now have a Singularity container that can run Singularity inside of it, and we're running 48 vCPU Singularity containers with them with 96 gigabytes of memory, the CVMFS mounted, and they get 860 gigabytes of scratch storage. We've been donating actually over 1 million vCPU hours a week to to OSG. We've been donating about 2 million, but I've told Frank that we're committed to donating at least 50 million vCPU hours this year to OSG, and we're on track to do that. We're working with them on improving the utilization of the hours that we provide, and that's an open topic, that we're going to work on with them. I think it's going to be starting in May is when their team's going to swing around to working with us on that. So I want to spend just a moment on the CCSTAR program. Frank and I talked that this might be something that this audience would be interested in, and how you could use cloud computing in the CCSTAR thing. Now, I want to stress that what I'm about to say is taken off of last year's RFP, and I looked and I couldn't find a new one for this year. So I'm not actually sure whether they're going to do this program this year. There may be somebody on the call from NSF who might be able to answer that. So basically that program, section 4, part 4, was $400K over 2 years. And I took some snippets out of that section. Proposals are required to commit a minimum of 20% of shared time. You guys can all read on to an external shared organization, and they explicitly mention the Open Science Grid in that. And they also have a sentence that says that campus computing solutions that integrate cloud services are particularly encouraged. So, if you look at how that could play into it, if you're thinking of doing a CCSTAR proposal, we have a good working, I think we have a good working relationship with OSG, and Brian seemed to indicate so in what he just said. And we can handle providing OSG with their compute resources needed to satisfy your commitment there. And that eliminates your need to set up and manage the OSG software on your equipment, pay attention to the stream of OSG security notices and update your container notices and stuff like that, and just generally simplify your life a little bit. There's other advantages, of course, with working with a cloud vendor. I'm waiting for this to catch up. Yep. Oh, they clipped that off. I apologize. So, the RFP explicitly allows use of cloud resources. I think, that we're the lowest cost, most environmentally friendly cloud provider out there. Our on-demand, at the on-demand rack rate, which by the way, you will never pay, that's 40 million core hours, 80 million vCPU hours. If you get lower qualities of service or use our OSG special pricing, which I'll show you in a minute, you're going to get even more time on that. And the advantages that we have are the advantages that any cloud has over buying a pile of hardware. You can run far more jobs on our resources than you could at any instant than you could on however much hardware you could get with $400,000. You're just not going to get the node count that you can have access to. The obvious advantage, if you're not using the resources, you're not paying for them. And oftentimes at lots of schools, and certainly was true at UVA, you're not always utilizing your resources at 100%, but yet you've paid for that time. And when you don't use it, it disappears. Of course, you can add GPUs, which only a few of your users might want. And the other users might not care for that. And then you don't have to do it with the system administrator time. I've talked to some people at smaller schools where they don't have a tremendous amount of system staff to work with their scientists to help them understand how to use these resources. And from from that person's perspective that I was talking to, their human resources are precious. They want to use them on helping their users onboard, not keeping the hardware software stack operational, which can take up a lot of time. So I said there was going to be an OSG special price. So in here I've got our rack rate, which you're not going to pay, is a penny a core hour. We're going to for on demand for OSG, we'll give that at 0.8, and if you do best effort with OSG, it'll be 0.5 cents a core hour, which is, it's above the price of the electricity, in most cities, but not a lot. If you want K80s, our rack rate for those is 10 cents a pop, 8 cents a pop on demand. In other words, as long as you want, 4 cents a pop on at best effort. A6000s, those are, if you have users who need a lot of VRAM for their machine learning applications, the nice thing about the A6000 is it has 48 gigabytes of VRAM. And they're not cheap, and they're not cheap on Amazon either. So that's $1 an hour full rate and 40 cents down. And you can get these terms if you wanted to submit a CCSTAR proposal. And certainly, I'm going to speak for Frank for a second. If you're interested in going down that path, you might want to work with the OSG folks get it all together, and we'd be happy to work with you on that. Or actually, for anybody in this community in the next 6 months, if they ask us for that, I'll go ahead and give that away. The stuff won't start coming online at the renewable sites until November, December, January. But we have plenty of resources in Houston in the interim. So to kind of wrap it up, and I will, wow, I'm actually going to stay at 25 minutes, just barely over. I'm kind of amazed. The message that I hope I've given you is there's a massive amount of renewable energy going on, and there's a transformation underway that I think many Americans aren't aware of. Computation is one of the few industries that can really exploit the type of energy that renewables represent, because they have two major problems. Is that they're intermittent, so you have to be able to ramp your load if you want to onboard them easily, A, and B, they tend to be in the sticks in the middle of nowhere. We have a site that will be able to handle 2 gigawatts that I can't talk about the site anymore to say that it exists. The nearest town, the big city 10 miles away, 10, 15 miles away, has 900 people. So there's not a lot of infrastructure where a lot of the renewables are being generated, and computation is fortunate because all we need is electricity and fiber, and the Great Plains is lousy with fiber, and I can talk about why that's true. But fiber is incredibly cheap out there. We're building renewably powered data centers in the Great Plains. Right now, we're starting in Texas, but we're already starting to look in other states and on where we're going to land those. We have a demonstrated ability to run high-throughput OSSG jobs. We also just recently finished a test for US CMS, and they seem to be happy with the test and are looking to do some experiments with bursting onto our infrastructure. And I don't think you're going to find a better price for HTC cycles, than Lancium. And with that, I will turn it back over. And I only went 2 minutes over. I apologize for that.
Awesome. Thanks, Andrew. That was an awesome talk. I really loved it. So I think we have time for maybe one question. So please raise your hand if you do have a question, and then one of our helpers can allow you to unmute. Looks like Steve Tim has a question.
I can't hear anything.
Yeah, sorry, Steve, you're really quiet.
Are we going to see HQ counter support at any point for this?
Can you say that? Repeat that question again.
The question was, are we going to see HT Condor support for this at any time soon?
So that's an interesting question. So I don't understand the underlayers of OSSG really well, but I know one of the things that we were looking at doing.
So Andrew, I can answer. The short answer is yes, because we can sort it out. So OSSG can sort out the Condor support, Steve, and then you effectively have you submit to a Condor system or a CE or something like that, and right now it's run by backfill containers, and we're just committed to work with Andrew to turn this into a pressure sensitive container. So we could then use that to simply attach this to your favorite condo pool and provide it as a service. And so it's on the drawing board and you're going to see it. Does that answer your question, Steve?
Yes.
Okay. And just from a process question, we have a Q&A, another Q&A period at noon.
We have a Q&A period a little bit before noon, but we're kind of
running
stealing. Yeah, we're stealing that time, but we do have noon. We will keep this room open between noon and 1 p.m. So if you're interested in sticking around, I also noticed that there are a lot of questions in chat. So if you want to take a look over those, there's definitely a lot of stuff about the renewable side of the house.
Sure.
Yeah.
Okay. Great.
All right. Thanks so much, Andrew.
I will stop sharing as soon as I find the right place, the right button. There we go. I think I've stopped.
Oh, and actually, Brian Bockelman, I saw that you had your hand up. I think we have time for one more question.
Yeah, I wasn't sure. We're trying to hurry us off the stage. Andrew, you mentioned network connectivity and that the new sites are planned to come up at 100 gigabit.
Right.
There's network and then there's already network. Are you planning to coordinate with folks like Internet 2 or ESNet to set up?
Right. So I'm not the networking guy. I know that at the new sites, we can pick our peers, our peering at the network hotels. And this is a little embarrassing to me. I'm mostly repeating phrases I know, not that I have deep knowledge about. And one of the things that we've looked into, if it becomes appropriate, is peering, for example, with ESNet. With Internet 2, I don't know, because I don't know the rules that those organizations have to peer with them. But on the new sites, we're basically going to be going into a network hotel, and who's ever in that spot, we can then peer with. And that's not really the answer you probably want, but that's the best answer I can give you because I'm not a networking guy.
Yeah, I mean, I was just thinking of potential roadblocks, and at least on our campus, I think it's a factor of 20 of bandwidth to R&D networks versus commodity internet.
Right. Okay.
Alrighty. Thanks again, Andrew. That was great.
Sure.